operating plant. And that particular lesson or that approach or that culture is something that is very rare today.
Thank you.
And now let us go on to number 6 here of our 7 topics, which is the operating organization. And we had a superb one, and that started with our client and went through to Westinghouse. So let us hear from the client on how this approach to a good operating organization was developed.
Well, the head of operating organization, including a disciplined operator training and qualification program, supported by strong engineering and maintenance elements located at the plant, with strong backup support from the laboratory organization, was part of the key to the success of the project. In establishing the operating organization, the laboratory borrowed from the nuclear power program of the Navy in several aspects, including the matter of operator selection, training and qualification, and the sustaining of the discipline of that process. The operating organization also was made successful by having readily available key engineering support and maintenance support in a smooth operating process. As Bruce has alluded to, the operator qualification was a key part of success, and sustaining that, keeping it going throughout the life of the project was key to operating to a successful operating period.
And Bruce, do you care to add anything here? Because you were there at the beginning of the
Well,
operation.
yes, we had a superb operating team. This showed not too long ago with a picnic get-together of the FFTF gang, and people were proud to be part of that. They saw it as an experience in their own lives that was unusual. I know that's true of myself. Very, very difficult, but very, very enriching. And the best part for me was being able to build the organization in the field for this testing and these operations and the maintenance. One of the primary decisions there, again, was to have operations know that they own the plant. That whether it's maintenance coming in there to do a periodic maintenance job, or whether they're correcting a fault, or whether they're doing an acceptance test, they must do it in accordance with operations wishes. So operations felt strong with their role, and they did the job of documentation to a wonderful extent. We'll talk about that in a little bit. They were a service group to the test engineers who had to conduct the tests, and operations enjoyed that. They were responsible for the in conducting of all of the periodic tests that were needed in the plant. These tests involved change notices in many cases, and engineering changes to a system after the startup testing was over with had to fall on the operations and maintenance back. They had to keep credit, take charge of all of the changes to the systems from that point on. Not only system changes, but procedure changes. They have the operating manual, the procedures for the various systems. If there's a change in the book, record for that system, it's a procedure change which they must document and validate and confirm it by test. And so that they had to be people that were comfortable doing the particular job, doing the detailed job, and having the records show the completion of it. In doing their work, they benefited by having outside help. Operations needs to have a standards lab, for example, close by. They don't operate the standards lab. The project didn't have a standards lab. Battelle had the standards lab. Battelle provided an enormous amount of help to the head organization and the operations team by their facilities. Security guards and specialty safety people were available. The training program and the qualification to become an operator was severe. They did have, and they established this themselves, the leadership, to make it be a very, very thorough test program, very legitimate, and had them qualify. It was not superficial at all. I think a lot of this was due to the fact that these were people that had come out of this background of the nuclear Navy program, had done the work in other places the same way. We had high attrition because these were people in high demand elsewhere as the nuclear program was building in the United States. We lost a lot of good people during that period of time through attrition. So we had to keep it ongoing. The training program was continuous. I think those are my remarks on this topic. I'll turn it back to you now. Okay?
Well, let me just piggyback this. We were very fortunate, I think, that at that time we were able to attract a lot of Navy personnel who had run the subs, and they had a discipline that Rickover had so carefully set up. I suspect that Rickover learned all this from Bruce Nordhoff here, but he's too modest to take credit for that. But in any event, that's a fleet that basically we don't have now, and I think we need to recognize that the kind of people that are going to operate a plant do need to be very disciplined. They need to be very, very well trained. It is something that I think the present nuclear renaissance is going to have to take under very, very careful scrutiny. How do we attract people that in fact have this can-do attitude, have the technical background to do it, and will take ownership, as Bruce pointed out. Now, Ron indicated that Bruce and Dave here were a little immodest. Let me say something about the good Dr. Omberg over here, and this has to do with training. These reactor operators all had to endure a Dr. Omberg course in physics. And I can tell you, they understood what was going on. It wasn't just a matter of if this happens, press this button, if this goes up, this button. They understood the basic physics, how a reactor operates. That is absolutely crucial, as we know from the 3 Mile Island accident and so forth. And the operators didn't really understand what was going on. They made exactly the wrong decisions. And we have suffered, the entire world has suffered because of those kind of concerns. These operators, Ron is probably one of the most skilled teachers I've ever encountered, and they had the benefit of that. So they knew their business. I want to share just one story regarding discipline. This was later in the project, after all of the plant had been running for quite a while, but we wanted to do some safety tests on the reactor. Now, it's quite easy when you actually have an operating reactor and you put it in deliberately into a transient mode, a protected mode, of course, but into a transient mode. You can determine what the reactivity feedbacks are as a whole because the reactor operates with all that integrated. But how do you separate the Doppler coefficient from the radial expansion coefficient, fuel axial expansion coefficient, all these kind of things? We had a running reactor. Is there some way that we could pull this out, not only to understand our reactor better, but to in fact impart confidence to an input to Clinch River or any other reactors coming online? And so we had a fairly extensive safety program. And one of the tests was to in fact bring the reactor into a certain configuration, let it sit there for a long enough time to get into complete equilibrium, and then take the measurements and so forth. Well, at one time we had several people from national laboratories. I think Brookhaven, Argonne was here, and we had a couple of people from the Department of Energy. And we brought them out, not in the control room, but right next to the control room to actually witness some of this. So they could see this wasn't fabricated, this was real stuff. And they all had busy schedules, you know, had airplanes to catch and so forth, but the reactor operators were instructed that they bring the plane into a certain equilibrium, and it had to stay there for a period of time, and oh, they didn't quite get it right, so I had to move the rod just a little bit more, and all this takes a lot of time, and I was getting kind of antsy because, oh my God, you know, these guys they're going to have to spend another night here, whatever. And it was about 3 o'clock in the morning before they finally said, okay, things were ready to go. And I was feeling that I needed to apologize to some of these people, and they came back and said, absolutely not. They were so impressed that it wasn't a pressure of time. These operators were going to do it right. And I think that speaks volumes as to what happened. These guys knew what they were doing. They were extremely disciplined. They understood what was going on. That was a safe plant, and partly because it was a well-designed plant. Undoubtedly, but they ran it very, very well. They had discipline that was absolutely almost unreal, and I feel like that we owe an incredible debt of gratitude to the people that were hired to do this, that were well trained. They ran this thing very, very well.
One thing I think I'd like to point out, and most of the operators that operated FFTF were very technically sound, and as a matter of fact, many of them were actually degreed engineers that came into the program. And when we got them out here, then they went through a very detailed training program as identified, which took about a year at least to accomplish before they ever really were turned loose in the reactor on their own. They also had the advantage of we had a simulator right there on site that was in every aspect an identical unit that was in the reactor building itself, and therefore they could simulate accidents, they could simulate off-normal incidents, and then watch and see how the reactor operator trainees would respond to those. So that we had all that out there and had that advantage, I think, to train all those operators. But the operators, like I say, were very, very technical, and some degreed engineers. They went through that training program, and I'm sure every operator can relate to some of the oral boards that took place in order to make sure that they knew what was going on. And as was alluded to, they not only knew how to operate, they knew why they were doing what they were doing, and they knew what to expect when they would perform an activity. They knew what to expect to see as a response, and if they didn't see that response, they knew they needed to do something different. And that, I think, is one of the key issues in the operation of the plant.
One point, I guess, that came out in this discussion that's worthwhile emphasizing, and that is maintaining throughout the operating life of the plant a disciplined, well-organized operations organization, engineering organization, and a safety organization. And Alan referred to it when he mentioned the passive safety tests that were conducted at the end of the plant's life. These were unique tests. Nowhere in the world had they ever been conducted before. The architect or driving force behind those tests was Alan, working with operations and engineering. Alan was in safety at the time, the manager of reactor safety. The tests involved tripping the reactor pumps, shutting off the reactor pumps so there was no coolant flow to cool the reactor, letting the reactor go on its own transient, okay, and ultimately shutting itself down to demonstrate that, in fact, it would shut itself down if, in fact, you should ever lose power to the reactor plant and the primary pumps. These tests were performed successfully, first time ever on FFTF. A tribute to the organization and to Alan to show the extent to which this was unique. The French just shut down Central Phoenix. They wanted to perform a set of similar tests, but they did not. They could really never quite get it together in terms of organization, test design, and test operation. So that was a unique experience in FFTF, even at the end of the life of the reactor. And I tribute to the organizations involved.
You know, if I could just take a minute to a personal anecdote on that. I indicated earlier the particular incident that or situation I referred to were very controlled situations where we just simply wanted to keep the field temperature constant so that we could measure things other than Doppler feedback, or we would change the field temperature and do something else. Those were all very controlled. But Ron pointed out the last set of tests were actually conducted to see what would happen intrinsically if the plant protection system didn't work. Now, if you understand, when in doing safety analysis for any type of reactor, of course a plant protection system is designed so that any incident that you can think of is protected. That's what the plant protection system is for. The control rods drop and the power goes down and whatnot. But one always has to ask what happens if it doesn't work. What happens? I mean, you know, as Murphy would say, you know, if it's mechanical, it will fail. And so you have to look at these kinds of end-of-spectrum accidents. And part of my responsibility was I tell people I used to blow up reactors on a computer. We had to do these by simulation, of course, and so we did a lot of these. And this was not unique to this reactor. It's done in every system. But we certainly had the very distinct impression. In fact, we knew that if the plant lost coolant, if the pumps coasted down, there was no coolant there, and if the control rods didn't go in, we would get into sodium boiling and cladding melting and so forth. And we went through these kinds of scenarios, and we proved, if you will, to the satisfaction of the Nuclear Regulatory Commission and the Advisory Committee on Reactor Safeguards, which is even a tougher group, that we had sufficient containment, even in this end-of-spectrum accident, that the public would not be damaged. But having gone through those, as Ron pointed out, then Jim Waldo had a very nifty, these were clever people, Bruce, that you hired, or maybe this was Chuck, I'm not quite sure, but in any event, came up with a device which was called the GEM, a gas expansion module, and the idea was to simply take a duct, if you will, it was capped on the top, and you stick it in the periphery around the core, so when the sodium pumps are on, the sodium pressurizes that, and the pressure builds up because it's capped off. Well, in that case, the neutrons hit the sodium, they bounce back in, and we maintain criticality. But if the pumps go down, the